Okay, good morning, Professor David J. The date for today is September 19, 2023. The time is around 7:30 a.m. Okay, my discussion for this session will be a continuation of my long video format discussion on alternating current machines, and this will now be lesson number 15. This is a very interesting one because this topic is the topic on how to compute for the equivalent resistance losses, reactance losses, and impedance losses of a transformer. Okay, let's proceed. The topic for this morning will be alternating current machines, lesson number 15, and the title of the topic is short circuit test of transformers. Short circuit test, what do you call this in simple words? It is the test that actually compute for the copper losses of the windings of both the primary and secondary of transformers. So if we say short circuit test, excuse me, it should compute for the copper losses. Copper losses meaning the resistance, the losses due to the resistance of the windings, the reactance of the windings, and the impedance of the windings. Because there are two losses for transformers, the so-called copper loss and the core loss. Core loss is actually due to the so-called lamination loss. Lamination, it's the core in which the winding are wound, right? The loss for that is actually termed to as core loss. But the other loss is actually the so-called copper loss, and copper loss involves the resistance of the winding and the reactance of the winding. So of course, if we could compute for the resistance and reactance, we could compute for the impedance, and we could compute for the percent regulation. Okay, let's proceed. The circuit diagram for a short circuit test connection will be this. We are just given the, what they call this, single phase transformer. This is the secondary side. This is the primary side. Okay, look at it very clearly because these are the proper connections on how to determine the copper loss. On the primary side, we will connect a voltmeter over here, designated by the voltmeter. Of course, it's an AC voltmeter. And in series with the primary line, in which it should measure a current, in series with it is an ammeter. Of course, it is an AC ammeter. And again, in series and in parallel, after the ammeter, we are given a wattmeter. Wattmeter is just an equipment or gadget that is a combination of an ammeter and voltmeter. That's why if you try to look at it from the diagram, this portion here is the current winding, and the winding that's below is actually the voltage winding. So for a wattmeter, it's a combination of an ammeter and a voltmeter. But other than that, we got another equipment which is ammeter and voltmeter connected separately. So actually we are given, there should be 4 equipments here. Voltmeter, ammeter, wattmeter, and before the wattmeter we are given a rheostat. Rheostat is just actually a circuit component in which if you try to adjust it, you will adjust voltage or current. Okay, so this is a variable thing, you know. This arrow here represents the voltage here, meaning the resistance of the rheostat could be adjusted. It's just like the volume control, right? The analog, it's not the digital. Analog is just, we are given a resistor like this, in which if you try to adjust the volume, you try to rotate, okay, the knob, So rotating the knob, actually you will adjust it from maybe from 0 to maximum. So if you want the maximum volume, you put it here. If you want the minimum volume, you put it here by turning the knob. The same true for a rheostat. So if you want to adjust the use of the rheostat is actually to adjust the current passing air, the current going in. Right? There should be current going in. By adjusting this rheostat, we are actually adjusting the primary current. Okay? So, the voltage of the source that is applied, it's specified over here. The applied voltage here should only be under short circuit test. It should only be 5% of the rated BP. Because the voltage here without the rheostat is actually BP, right? But since we connect a rheostat over here, okay, we could adjust the applied voltage here. By adjusting the rheostat, we could increase or decrease the voltage that is coming in. But for a short circuit test, the source voltage will only be adjusted to 5% of the rated BP. If this is BP, what will be adjusted here is that actually it's only 5%. How come you know it's 5%? Supposing the primary voltage is 2400, right? And you want 5% of that one. 5% is actually 0.05, right? So how much is that one? I could multiply this one, but I don't want to make the board dirty, so I will just use my calculator. So this will be 5% of 2400 is 2400 times 0.05. Okay? This should be equal to 120 volts. Okay? So if the rated primary voltage here is 2400, to perform the short circuit test, okay, you will adjust this rheostat here such that the voltage that will appear here across this terminal is 120 volts. Right? Let us go on the secondary side. On the secondary side, there is no load. This is the secondary side. And actually, we shorted the secondary side. We shorted it. We put a shorting wire. Okay, we connect this one and connect this one. There is no load. We short circuit. This is a shorting wire. That's why the title of the subject matter is short circuit. Okay, we short the secondary and we perform or we place all the gadgets on the primary as like this. We got the voltmeter here. We got an ammeter. We got the wattmeter. We got a rheostat. The purpose of this rheostat is actually to adjust the current coming in to the rated IP. Or actually, if this is 100 kVA, okay, you multiply 100 kVA by 2400. I think we have computed this one the last time around. It is 41.67 amperes. So to perform the short circuit test here, okay, you will adjust this rheostat here such that the current that will be registered by the ammeter will be 41.67 amperes. Okay, that's the what they call this mark point on how to perform the so-called short circuit test. So after shorting this one, to get the correct copper loss of the transformer for both the primary and secondary, you adjust the rheostat such that the current passing on the ammeter will be equal to 41.67 amperes. If the rating of the transformer, this is only an example, right? 100 kVA and the input voltage, so the primary voltage here is 2400. We computed this time, the last time around, right? Okay. Okay, I will go back to the annotations now. Actually, what I discussed is actually the one being mentioned in the annotations, right? Annotations is just a summary. Okay, I will try to read it. The secondary terminal short circuit the secondary terminal is short-circuited. Step number 1 is we short-circuit this one. Step number 2, the primary side impressed voltage is 5% of BP. Okay? You impress only a voltage here, the magnitude is 5% of BP. Number 3, this is just storytelling now. The mutual flux is the same at 5% BP. This has been done by experiments by engineers, and if they perform the short circuit test, the mutual flux at 5% is actually the same at full load. So even though the impressed voltage is only 5% BP, the mutual flux is actually the same as if the voltage is equal to only BP. That's the meaning of that one. Number 4, the mutual flux is directly proportional to the core loss. Okay? Engineers say that at 5% BP, the core loss is 0. Okay? Core loss. The loss due to the so-called lamination, the movement of the flux and the conductor, right? So at 5% BP, engineers performing the short circuit test tell us that the core loss is 0. So if the core loss is 0, what will be registered here on the gadget on this primary only refers to the so-called copper loss, the loss due to the winding of the transformer due to its resistance and reactance. Number 5, what meter will only register the copper loss since there is no power output or core loss? That's the one I'm telling you. Okay? The power that will be registered by the watt meter in terms of true power will only be the copper loss. Copper loss is actually the loss due to the reactance and resistance of the windings, because whether we like it or not, there is no perfect thing as winding, right? There should be a small resistance like what we have computed from lesson number 14, and there should be a small reactance, right? Number 6, the rheostat adjusts the primary current to rated value. I think I've told you this one already. The purpose of the rheostat here, okay, to get the correct copper loss of the primary and secondary winding, adjust this one. So when the current passing here is 41.67 amperes, okay, the rated primary current, okay, stop at that one, because at that current reading, there should be a reading for the watt meter, and the reading for the watt meter is actually the copper loss of both the primary and secondary. That's the correct value. Okay, number 7, the rated current will also flow in the secondary by transformer action. Okay. That's transformer action. If there is current here, I don't know why I bring up this one. The watt meter registers only the copper loss in both windings. I told you this one already. Okay? So, the annotations, it's the first one that I have storytelling you about you already. That's the concept on how to perform this short circuit test. And there are formulas on how to compute for the equivalent resistance and impedance, okay? Because with the readings on the primary side, we got the ammeter reading. The ammeter reading here is termed to as the short circuit current, ISC, capital letter I with the subscript SC. The voltage that will appear here will be the voltage, capital letter E with the subscript SC, meaning short circuit voltage. The reading on the watt meter will be the total true power consumed by the winding of the transformer. We needed one in the computation. What's next? For the rheostat, there is no reading on this. You just adjust it such that the current that will pass here will be equal to 41.67 amperes, the rated primary current. Okay, so there is no reading on this one. You just rotate it, and as soon as the rated current is registered on the ammeter, stop rotating it. Okay? Okay, let's try to bring out the formulas on how to compute for the equivalent resistance. Actually, we'll do first, we could not compute for the reactance. It should be the resistance first and the impedance. For the first equation, the total capital letter R with subscript A, meaning the total equivalent resistance of both windings. We are talking both windings already. It should be capital letter P with the subscript C, meaning the total true power short circuit. SC is short circuit, it's not Supreme Court. SC here is the wattmeter reading. It's the reading of the wattmeter, right? Over I short circuit quantity square. Okay? This I with the subscript SC is actually the reading of the ammeter. Right? So this is in ohms. How come this equation came out? It's like this. If we are talking resistance, power is equal to I square R, right? So if we try to compute for R, it should be power over I square. So under the short circuit test, I will now place the proper subscript. This is with the subscript E, this is with the subscript short circuit, and this with the subscript short circuit. Meaning, the equivalent resistance of the primary and secondary is the reading of the wattmeter divided by the reading of the ammeter, but we must have to square it because this is a square. Right? So RE will be PSC over I short circuit quantity square. It is this. Okay? For the equivalent impedance, okay, we'll try to reach this one. For the equivalent impedance, we know that voltage is equal to current times impedance, right? So if we try to compute for impedance, impedance will be voltage over current, right? So if we now try to place the proper subscript, if we place E here, okay, this voltage here will be short circuit voltage, and this is short circuit current. Okay, this short circuit voltage is the voltage that appears on the voltmeter, and the short circuit current is the current registered with the ammeter, which is connected in series with the primary line. So by dividing voltage, short circuit voltage divided by the short circuit current represents the equivalent impedance of both windings, right? That's it. So how do we compute for the reactance? For the reactance, no problem with the reactance. This is RE, this is XE, and this is CE, right? A right triangle. We computed this one already. We computed this one. So if we are looking for the reactance, okay, Pythagoras principle. The square of this should be equal to the square of this plus the square of this. And if we try to compute for this, XE now will be the square root of the impedance quantity square minus RE quantity square. And the unit is still in ohms. Okay? Oh, that's it, guys. So for a short circuit test, by using the reading of the wattmeter, ammeter, and voltmeter, we could compute for RE, we could compute for CE, and by using this formula here, we could compute for the inductive reactance of the winding. Okay? Where PSC is the reading of the wattmeter, I short circuit is the reading of the ammeter, and A short circuit is the reading of the voltmeter. Okay? The reading of the wattmeter, reading of the ammeter, and reading of the voltmeter. From these values, we could compute for RA, ZA, and by using this formula, we could compute for XA. Okay, that's it, guys. That's the way on how to compute for the copper loss of a transformer by using the so-called short circuit test. Okay, good morning from Los Angeles. Professor David J. DelosReyes.